Hello and welcome to this video version of Lab 8. Because of the shortened week due to reading week this year, even though it wasn't a full week, we didn't get a chance to go through this in lab, so I thought I'd put together a little video solution just going through the solution you've been given already on Canvas. I'm kind of explaining what's going on, and then also going through a workable C solution so you can see what it's like to really program out the solution to this lab. My name is Michael. If I'm not your lab TA, I'm one of the TAs of the course. Hoping to do this in about 20 minutes or less. That's not how long I would expect the lab to take, but I'll just be jumping kind of right into the solution. You'll have a chance to pause the video and then work through things on your own. But yeah, I'll be going through the answers, hopefully explaining things clearly, and also releasing this sort of online file edition so you can really hack together the solution rather than just writing it out on paper, which is a little bit more fun. So before I get into it, I just want to explain sort of what's going on in this file structure. So what I've done is I have a solution folder, so I wouldn't look at that until you're finished. But I also have this source folder that contains a sort of custom makefile, and it can make each of the parts of the question. So we have one question today. There are 5 different parts, and you can run a command to make each of them. So for example, if I finish the part I, then I can make lab8I, and I can run that, and right now it's going to print out nothing, but just so you're aware that exists. This makefile is a little bit complicated and actually took me some real thinking to put together. So I also wrote a little tutorial on makefiles that I'll be releasing at the same time as this video and hopefully this lab starter. So just stay tuned for that. I created a header file that contains the definitions for each of the main methods and also a helper that prints an array, and then created a .c file that implements each of those kind of core methods that we'll use in each of the steps of the question, and then starter files for each of the different parts that contain global variables. Because each part is in its own file, I had to sort of recreate some of the globals. So for example, and that's annoying, please go away. In the first part, it asked you to make a array C, and I just had to make a fake C for part 2 because we don't have access to the part 1 stuff. Hopefully that all makes sense. Again, you'll see me kind of work through it. So if you get stuck, just feel free to watch me solve the first question, and that should make sense for the rest. You will need a sort of working GCC compiler. You can try uploading this to the servers if you want and doing it there. I'm on WSL right now on Windows 11, actually, you can see, so very fun. Okay, so getting into the lab, again, I'm going to move a bit quickly, but hopefully you've had a chance to at least look at the lab beforehand. I'm assuming you've paused it, tried it on your own, and thought about it. The way I approach these sort of dynamic control flow questions, it's a bit like in 110 where we had access to map and foldl and all those things. But this time they have really obscure names and we're told to figure out how to use them. So let's just read through each of the methods and get a sense of kind of what they do. So first one, void m, takes a function pointer and 3 integer pointers. You can look at the method and see kind of immediately that they're dynamic arrays. You can also tell from kind of the int n, it's the size of the array typically. So it's a good guess that these are probably dynamic arrays. And we say for I from 0 to n, set c sub I equal to applying f to a sub I and b sub I. Okay, so this, okay, the one thing is the first letter is M, so it kind of restricts your range of guesses. And in fact, this one is actually map, kind of like a map. The one thing that separates it from a normal map is that we're working with 2 elements. But if you wanted to just ignore B, you could do so. So you could set some kind of dummy array B and then have F ignore the second parameter every single time, and then you'd end up with normal map. So this one is like map. The second one also takes a function pointer, takes probably a dynamic array again, int n, and this time we have some p. And p, you can see in the for loop, acts kind of like a result so far accumulator, which again, sort of going back to that 110 knowledge, hopefully it hasn't brought up any PTSD for any of you or anything. And so yeah, we have this result so far accumulator. We're going through the whole array, reapplying f. I'm not sure if this was in 110, but it is a bit like a JavaScript array method that I'm pretty familiar with called reduce. So on every single iteration, we kind of update the value of p depending on the new value of a. So common things you can do with this are like counting. So you could, for every single value in a, you could just increment by 1 every single time, and you'd count the number of elements in a. Last one we have is fi. So it takes a function pointer, 2 dynamic arrays this time, int n and int p. We have a kind of counter. We can see we have j and then j plus plus, j, and we return that in the end. So that's interesting. And we loop through the array again. if f, so f is kind of like some condition, then we set b to a sub I. Now what's interesting here is we have the j++ inside. That's just kind of ugly C code, but it works. So what it does is it says b sub j equals a sub I, then it does j++. Just be aware of that. It's a little kind of catch-22. First we do b sub j equals a sub I, then we do the j++. If you wrote plus plus j, that's also valid C, and it would do the increment before setting the value. So it would do plus plus j, it would increment j, and then it would set b sub j equal to a sub I. So I would prefer these broken into two lines and have the j++ after, but fine, this is a nice way to sort of, I guess, shorten the number of lines if that's what you're considering to be clean code. So this one, fi, again, a bit of a hint. This one is a filter. So for every single a sub I, we're checking some f, and we have this optional p, so we can do fancy things with that p. And then if it's met, then we add it to the b array. And we also return j, so we know the size of the b array in the end, right? The rest of b is going to be kind of nulls if we didn't use them, but we know that we set b from 0 all the way to j when we're finished. Okay, so those are the three methods, again, in a nutshell. If you didn't totally get all of that, don't worry about it. Again, I have a little bit of, sort of, M, map, R, reduce, FI, filter. That's just a bit of a trick and really helps. But if you didn't get that, it's not important. It's just about can you apply them in the questions. So without further ado, why don't we get into those? So the first one asks us to store the sum of elements from A and B into an array C. So this one, again, just went over them. You're storing sums in a new array. You have two arrays you have to work with. Also, the arrays are called A, B, and C. That sounds very, very familiar to M, right? Here we have A, B, C, and M. So I'm going to go ahead and work with M. The first thing I need to do, of course, is to sort of initialize C. So I'm going to say C equals malloc. And there's a number of different ways you could do this. I think we're given N. So you could just use some n, and here I've defined that actually. Also, since a and b are static, you can do this little trick that I'll show you in just a moment. So we could say n times size of int, right? And so it'll give me n ints times each int is 4 bytes. Then I'll get an array the size I want, in this case just 2. I could also do c equals malloc size of the whole array, which is a, divided by size of a thing in the array, typically the first element. So the size of the whole array, in this case, is 8 of 2 bytes, and the size of the first thing is 4. And so that way I can figure out the size of the array sort of on the fly. And if I change this to being a char array or something, it will still work, which is kind of nice. So that's a nice sort of flexible way of saying n, and then you'd still have to multiply by size of int. And you'll see that sometimes in C code, it's common. Okay, so now we've initialized C. Let's make a call to M. M takes an F. So we haven't defined F, but we know we're going to be adding two elements. So I'm going to guess the name is going to be add. It's going to take A, B, and C, and then finally N, which I've set here, capital N. We need to define N now. If you're stuck on how to write your helper method, the easiest way to get going, a bit like in 110, is to steal the signature from the function pointer. The function pointer is kind of a freebie because it tells you what the signature is, and that's often a good first step. So I'm going to steal that. And then I'll just get rid of the kind of strange syntax that C uses by default. Okay, so now I have F. I want to call it add instead because it's more descriptive. And what should add do? Well, it takes two integers. It's called add, returns an integer. Just return A plus B. Not too bad. And after that's all finished, I probably want to check the value of C to make sure I did everything okay. So I'm going to do print array of C. Oh, this is complaining because I forgot the size. It is a dynamic array, so I need to know the size. I think that should be everything. Now I'm going to make lab8 of I. No errors, which is awesome. Good start. Print that out, 3.5 as desired. So that's the first question. From here, hopefully you have a sense of like how to do the rest of the lab on your own. If you haven't already, you can pause, go try it. I'll still be here when you come back. If not, I will move right along now. The next part asks you to determine the maximum value in the array C computed in part I. So I've given you fake C, which are 3, 5, like the correct sums from before, and we want to store the maximum value in MX. So again, like for my intuition, if I do a lot of JavaScript programming, that's what I did on co-op, I would be like reduce right away. So I have a function that does reduce for me. That's great. If that's not how you approach the problem, that's fine. You could also look and be like, okay, I need to return a single thing, not an array of things, and M sort of sets an array. J returns a counter, but is also kind of setting this B array, which I don't want. So R kind of becomes the choice by default in that case too. So yeah, we're restricted to R, and why don't we just start there? We can start with a call to R. It's going to take a function. Let's think. What do we want it to do? Well, we want to return the max in the end. So this function hopefully will update P to be the new max, right? So why don't we have a function called max? It's going to take two things. We need our integer array, which in this case is fake C. The size, again, is capital N. I've defined it for you. And then the last thing is P. If I want the maximum of an array, I need to figure out what to initialize P to. Like on the first iteration, what should P be before I've seen any elements? A natural one is negative infinity, right? It's like nothing at all. It should be the smallest possible value. We don't really have a nice way to do that in C. Like in, I think Python, you can say something like float negative INF or something, and other languages have something similar. What we can do is set the smallest possible integer to be this value. And the way we could do that is with int min. And you can see I've kind of given you a hint at the top there. You didn't have to do this way. You could also do negative 9999, whatever. Hopefully it doesn't overflow. But int min is like a safe way to do this. So that's from limits.h, which again, we can just go take a poke at if we want. File was a part of GCC, very cool, and there's all kinds of fancy constants in here, short min, short max, and int min, and long min, and so on and so on. So here we just use int min, and that'll work fine because, again, P is an integer. Okay, so we need to define max, and let's say, again, I'm going to just copy the function signature. That'll help me get started. Takes int A and int B, and it should return the bigger of the two. A nice way, you could have said, like, if A greater than B, return B, oh, sorry, return A, and so on. But there's actually a short one-liner to do this, and some of you may have seen it before. It's called a ternary expression. The general syntax goes, it goes your sort of condition, question mark, the value if it's true, otherwise the value if it's false. So this is like, if thing, return this, else return this, but we just do it with question marks and colons instead. So here, I want to return A if A is bigger and B if A is smaller. So my condition is A greater than B. And you might be wondering, oh, what if I have a tie or something? Doesn't really matter then, I can return either. So you could have said A greater than or equal to B, or yeah, other way is fine. So A greater than B is my question here, and if that's true, the answer is A, otherwise it's B. And I have to remember that R returns something, so I have to set that to the value of mx. And to check my work, I can printf #d /n mx. With that, I'm going to make 8. There we go. So you can see, it'll blow it up a little bit. Got the right solution for that one, which is great. I can minimize this too. Hopefully the bigger size is slightly more helpful. So yeah, it looks okay, but yeah, doesn't hurt. Okay, so that's part 2. We can move along to part 3 now, which asks us to allocate and compute two new arrays, E and O, and store the even elements of A and E and the odd elements of B and O, and then store their length, T, S, S, in N even and N odd, respectively. So a few things I have to do here. I know I'm creating a new array, which is a bit like M and Fi, but I have a condition, right, which says only the even elements of A and only the odd elements of B. So the most natural thing, again, is using Fi, filter. So I'm going to filter the elements of A down where they're even, and filter the odd elements of B down to O. And then also I need their lengths. Well, thankfully, Fi returns their lengths, right? It returns this every time I've stored a new element, like B sub j. I also increment j and then return j, which is really nice. So Fi will do everything I want here. I'm actually going to start from Fi again, do both of our calls. So in the case of our E array, we want a function like isEven. So I'll do isEven like that. We want to begin with the A array, which I've defined at the top for you again. B array is our target array, which should be E, but I haven't initialized it yet, so I better do that. And then I need its size n, which I've also given. It's 2 up here. That's the size of A, not the size of E. And then finally, I need some value P. Now, in my loop, I'm checking if A sub I is even. So P doesn't really matter that much. What you could do is, and this is jumping ahead a little bit, but just in case, is you could use P as a kind of is odd or even. You could take int A and P, and you could say return A modulus 2 equals P, and then set P to 0 or 1 depending on what you want it to do. But that's really ugly, right? It's probably better to just ignore P, because otherwise you have this really confusing function, and P could be all kinds of things, and you want to restrict it to just be 0 or 1, not really an integer. So yeah, I'll leave this because it's kind of interesting to think about. You probably didn't do it this way. I don't think the solution does it this way, but that's a way to take advantage of P, because otherwise it's just totally useless. So is odd or even, A, E, N, and then P, I would want to be 0, right? And if you're not familiar, this modulus symbol here, that's the percent sign. It means the remainder. So even numbers are always multiples of 2, so the remainder should be 0. Modulus 2 means that value should be 0. If it's odd, then it should be described as 2k plus 1, right, for some k. And so then A modulus 2 would be equal to 1, right? I'd have a remainder 1 after dividing by 2. So A modulus 2 equals 0 is even. A modulus 2 equals 1 is odd. P should only be 0 or 1. Not 1 factorial, 1. Okay, so that's for the E array. Then we'll do the same for the odd array, except we will do O. We still need B. We say N is capital N. In this case, P is 1. Okay. The next question is how big should A and O be? Well, you think in the worst case or in the best case, every single element in E is even and every single element in B is odd. And so I should set the total array size, the maximum size, so that I'm writing on memory I've allocated in any case, right? I kind of need to consider that biggest case. So what I'm going to do is I'm going to malloc A and B to n times size of int, right? That's the size of A and B respectively, and I actually think I've gotten the parameters backwards here, haven't I? This should be target array, so sorry, yes, I flipped these. So the biggest size E could possibly be should be E, is n, which is the size of A, and so I'm going to do the same for O. There we go. And then it says store their values in n even and n odd. So n even, right, that's going to be the result of how big the array is, and n odd here. And please forgive the mix of snake case and camel case. It's triggering my OCD. I can imagine it's triggering yours as well. So print array E size n, print array O size n. Great. Okay, so those are those two arrays. And then if their sizes are correct, oh, sorry, and these, yeah, should be their actual sizes. Making lots of mistakes on this one. If their sizes are correct, then the program shouldn't segfault. If the size is way off, like it's too small or too big, the program probably will segfault. So I don't need to print n even and n odd. This should be sufficient. I think I've done everything here. Let's try making it, see what happens. All right, no errors, which is always a good sign. And 2, 3, and let's check that makes sense. In A, my only even number is 2, and in B, my only even number is 3. So that's all good. All right, we can move on to part 4 now, which says determine the minimum of all the elements in E and O and store it in a variable called mn. We can assume that E and O both have at least one element, which is good. So this one's very similar to an earlier question. We want to figure out what the minimum is from two arrays. An easy way to do that is to start with our solution from 2, except do the minimum instead of the maximum, and then just return the minimum of the two arrays, right? That's kind of a natural approach. So what we can do is we can say R, and we want some function min, that takes, let's start with fake E, size n, and P, we don't know what P is, we'll come back to that. And then also the same thing for fake O. So this will give us the minimums from each array respectively. right? Again, very similar to part 2. So if any of this is a little bit too fast, feel free to jump back to part 2. But again, same condition here. I just want to return a less than b, return a else b. But the question here is, what do I set the initial value of p to? If you remember in part 2, we use int min because we wanted the maximum. So you probably could guess that for this one, we want int max. And that actually is a thing that exists. And thankfully, VS Code IntelliSense is helping me get there. So we have int max in both. Let's create some temporary locals to hold these kind of intermediate results. So this would be emin, and this next one would be omin, right? And the question asks for the minimum of all elements. So then all I have to do is just turn the minimum of both. So printf #d / n of, and I can use my helper again, emin and omin. Great. That's one approach. I'm sure there are other ways you could maybe try combining the two arrays and then just doing one call to R, but it doesn't really, enhance your runtime or anything. So it's probably easiest just to do what you did in part 2 twice, and then take the overall minimum of that. And this should be stored in mn too. So mn equals that results, and we'll print mn. Great. Let's make part 4 and run that. And we get 2, right, which makes sense because out of 2 and 3, the minimum is 2. And that would, work for larger elements. You can, of course, try that out, but should generalize well. Last but not least, definitely the hardest question out of the mix. It asks us to count the number of elements in C that are between kind of an upper bound and a lower bound. Now, it does say specifically mx and mn, and if you're paying a lot of attention, you might have noticed that in part 2, mx is the max of C. So all the elements are going to be lower than C at least, right? So yeah, you could kind of ignore that upper bound in this case, but I think that wasn't really the intent of the question, just kind of almost a mistake in how it was set up. So that is one way you could have approached it, would have been completely valid, totally the correct answer in this case. But I want to give you a harder problem, which is the general case of you're given some array, you're given some lower bound, some upper bound. How do you compute all the values between the two? Okay, so getting started with this one, we're going to need to do a few things. Like in the last problem, the best thing to do is to break it down into sub-problems. So I can definitely compute all the values greater than a bound or less than a bound, right, given what I already have. I have fi, and I know it can give me the result of a filter. And so I could have the filter just be checking against some lower bound or some upper bound, and that would work great. The problem is I want to be able to say something like int is between and have some a and then mn mx, right? And return is it between those two. So the natural thing to do is to break this down into two subproblems and say, first, let's deal with a lower bound and get some intermediate array, and then pass that intermediate array into the upper bound or vice versa. And then I'll have my final answer. So we'll go ahead with that. You could have done something like is between, because you could pretend mn and mx are global, and then you could have a and p and treat p as garbage, and then just say return fake mn less than, or sorry, a must be greater than fake mn and a must be less than fake mx. Right. This would have been a nice way of going about it too. So we've gone over two ways already. One is you could have ignored the upper bound because mx is already the max of C. Another is you could treat mn and mx as globals, and then you can kind of ignore p. The way I'll do it is probably, I don't know, the most correct, but it doesn't rely on mn and mx being globals, and it also doesn't rely on mx being the max of C, and is a kind of more general solution, and is something more similar, I think, to what's given in the kind of proposed solution. So let's do two functions, is greater and is less. So one is going to take int a and then p. And so p for the is greater, we want to be greater than the lower bound. So we're going to say int min, I guess. And we're going to return a is greater than that minimum. We're also going to have is lesser. which similarly is going to take some max, and it's going to say return a is less than the max. Now with those two helpers, we should be able to do our problem, right? Let's begin with saying, okay, let's get all the array elements less than the upper bound. So that's going to be a call to fi. We're going to say is lesser, right? Because we want elements less than the upper bound. We're going to have some other stuff, and then we know p is going to be whatever our upper bound is, which in this case is fake mx. Fi takes a, which is our target array, which is going to start out as really fake c. This is just some made up c array that it could be at this stage. And then we need a source b. Now the question is, how big should the source array be? And I'd like you to think back to what we did in, I think question 3 it was, where we said, okay, let's just set it to the upper bound, right? So we're going to do that again. So I can even just steal this line. We're going to have int star g, and that's going to be equal to the upper bound. The upper bound is the size of really fake c, and I don't have n, but I can define it. I can say size of really fake c divided by size of really fake c of 0. Great. Okay, so I know this lowercase n. So that's like if all the elements are, this should be star L, if all the elements are less than the upper bound, right? So that's going to be my target array, and then my size, as I said before, is n. That's the size of really fake c. This is going to be equal to int n lesser. Okay, so that's step 1. So now I've got a subarray, intermediate array, that's all the elements less than the upper bound. Let's do the same thing on that array for the lower bound. So int star g is going to equal malloc, and in this case my upper bound is n lesser, right? It's only the size of all the elements that were less than the max. And it's going to be size of int again. And int n greater is going to be fi is greater. And again, I want my subarray here, so this is L. My target is G. The size is n lesser. And I want fake mn here. All right, bit of a doozy, but hopefully that made sense. It's really similar. It's kind of a combination of all the problems we've done in the past, right? We're using similar knowledge to what we did in part 3, except now we're doing like we did in part 4, is breaking it down into 2 subproblems, and then not really combining, but feeding forward the solution from one into the other. That's kind of an elegant approach here. Not what you had to have done, but works well. In this case, it asks just for the count, which is the number of elements in C that are between these two. And that value we have immediately, actually. It's n greater. So we can do printf. I guess we can call it count, which is equal to pound d slash n. And that's n greater. Great. Now we're finished. No complaints, which is good. In the solution, it also has something to the effect of r, like it is something like int count equals r of inc, which is some like increment function, like I mentioned at the very, very beginning of this video. A, which in this case would be g, n greater, and p, which is 0. And what this goal of calling r is to just count for every element in G. So we initialize p to be 0. That's our result so far accumulator. And then every single time we just add 1. You don't need this at all because all this does is return you the value of n greater or whatever you put in this kind of third parameter. But so be it, we can do it. So it takes some int a, some int p, and in this case it ignores a and returns p plus 1. So that's another thing. And I'll just call this, let's say this is n greater, and this one is count. And let's make lab8v. You can see I'm getting a warning here because a wasn't used, but that's an okay warning. I'm fine with that. We print it out. We see 6 and 6, so we're all finished. And we can do a sanity check. If you look at my lower bound and upper bound, lower bound is 3, so it should be 4, 5, 6, 7, 8, 9. And then 10 is my upper bound, so that should be 6 elements, which it is. So I'm done. So that was Lab 8 in a nutshell. I think I went a little bit longer than I wanted to. I know I talked pretty fast, but you can slow me down, I guess. I'm the anti-2x speed tutorial. I'm already 2x speed. So hopefully that helped with your understanding of Lab 8. If you have any questions, post on Piazza. I'll be releasing this starter, which hopefully should give you some good exposure to C, good practice to kind of do this by hand. Not by hand, I mean by keyboard. And then, yeah, that should be everything. There's also going to be a Makefile tutorial coming out because this was actually pretty hard to write. Yeah, okay, so that's everything. Thanks for tuning in. Let me know if you have any questions.